Hello, I'm presenting here the second video of this series of videos where we are going to learn how to use the local volume mapper DAP and how to understand the data, visualize it, analyze it, and so on. All the videos are going to be included in this classroom that I will distribute. In this second video, we are going to focus on the installation, just on the installation. So this is it should be a rather simple thing. And all the installation instructions are included in the GitHub repository. This is the GitHub repository. I will include also in the instructions how to access to that. It's open. So we recommend that you use a Conda environment. If you don't know what Conda is and how to use it, you can go to the Conda documentation. It's a tool that allows you to create environments where you make a local installation with all the dependencies. And this is, for example, the installation instructions for Linux, but if you use a different operative system, you can follow the corresponding instructions. So if you don't want to install in Conda, you just do the steps that are in here. You clone the repository and install it, but we strongly recommend that you use in a certain environment, not to affect all the dependencies that you have in other tools that you may have in your computer. So I'm going to create a Conda repository in this computer where so does not allows me to copy in this way. Let's see if it allows me in this other way. Okay. So I create the Conda repository. Sorry, this has moved a little. Okay, it's going to tell you what's going on. So it's we activate the repository. Don't forget to activate the repository so you don't have problems with your dependencies. We clone okay, yeah, of course, that's I'm going to use a different directory. That was for the test. The directory name code. So there's nothing in there. And now we make a clone. Takes some minutes, few seconds. Let's go. Okay. We go in here and we install. So the program is going to install, this installation is going to install not only a Py3D, you're going to install the local volume mapper DAP is going to install a version of Py3D that basically is just prepared for being to work with the local volume mapper. If you have seen the previous videos, you should know what I'm talking about. Then just to be sure that you have installed the required scripts, you just need to run LVMDAP conf. It's the basic local volume mapper script. And as you can see, it has run it and it tells you what are, well, sorry. I have what I had down here. Oh, no. Oh, sorry. It's if you run any of the scripts that has been installed when you install the local volume mapper DAP, it's going to tell you what are the required inputs. This is a very, very basic information. The required inputs, basically, it's the local volume mapper file. It's basically a file that is produced by the data reduction pipeline. A label that is going to, is like a prefix or suffix that is going to be in all the output files to identify what you have run, and the configuration file that it's in the YAML format. I will devote a complete video just to explain the configuration file, so I'm not going to explain too much about that in here. So this means that the script has been installed. They should be installed in the local directories. So these local directories should go in here, local bin, and the basic scripts that has been installed are this one. This is the one that we have tested. That is the basic and the main script to run the tool. This other script that, if you follow my previous video, has the main aim is to create the model in case that you have run this script without extracting a model. And a third one that is to create simulations. There is another script that is deprecated, but it's installed in here. We don't recommend to use it anymore because we are not going to maintain hereafter or document it. So all the scripts has been installed just now. And of course, you need to have this directory in your path. So be sure that you have this directory in your path, because if not, nothing is going to work. Let's increase that so you can see in the video. So I have included in here, but depending on the shell that you are using, this is a different way to indicate where the path should be. Okay, so this is basically telling that we have installed the script, but following the instructions in the README file, it tells you to download some additional data. This data cannot be included in the GitHub repository just because it's too large. So it's in this GitHub, and you in here there is an example YAML file. As I told you, I'm going to explain the content in a different video. That's another YAML file. That is the current one that we're using to another configuration file. That is the one that we're using for running the full data set, so as to look for compatibility. This is an example of a real science data reduced with a non-optimal version. So there's no danger in distributing here because basically we don't indicate which pointer it is and so on, but no one can use for science. And in here there are the RCP templates that has been generated with the master library. In the future, we will include other libraries, as I explained in the previous video. These files, you can download them also for testing the fitting, to test that the script works. I have already downloaded them. They are in here. Samples, samples. Okay, so in here I download the files that are in here, the example files, two libraries, an example file for the configuration file. And we are going to use those frames in those files to test that the fitting works. I mean that the code is working. Following, well, here it's recommended that you create these environmental variables. It's not mandatory anymore, so you just recommend it. We'll skip that, and it tells you how to run some tests. Again, it's pointing towards this Google Drive to download the files that you require, and it tells you to place them in here. Okay, so since you are going to touch the directory where you are installing the DAP, where you have the load of the DAP. If you want to make any change in the code and pull and push and so on, first please contact me in this case just to know which branch are you using and so on. But remember that you have already altered, so you are going to create a discrepancy with the version that is on the repository. Okay, so we go to the examples directory data, and instead of loading again, I'm going just to copy the content. Actually, I'm going to copy the content of all these directory just to have all the files. But all the files are basically the ones that I tell you to download from here. So you just copying it. And now we have also, it tells you to run this file, but this file most probably is going to fail if you run it that way, because you need to edit this file in here. And most probably it's written somewhere that you should do that. Or maybe it's written here. Place it in here, copy the notebook. Well, okay, so okay, why it's written this way. I need to look to the README file, but you need to. I will edit that. You need to edit this file just to complying with your local directories. Because if you run that here, you have to go one step back and you run that as it is. What is going to happen is it's going to tell you that you don't have permissions for certain directories. No, there is no such file, but the file should be, let's see, example data. Yeah, it's the file is in there. Yeah, well, it's index here. It's written that I will modify. Okay, so it's a permission denied because it's pointing to a directory that is my own directory, my own installation, and therefore you need to tell the configuration file where to find all these files. No. All the files are in the legacy directory that is in here, but of course you need to point to your local installation to make it work. So you edit the configuration file, and wherever you find a directory that you don't, it's not in your structure of directories, you should modify for your structure of directories. So for instance, in here, obviously, this it's my directory, so you should change like this one. Okay, the fitting data, this is not the directory where we have stored the Stellar libraries. The Stellar libraries has been stored in sample data. Okay, this is the Stellar libraries that we want to use, so we need to modify that and indicate the right samples, blah, 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 blah. Okay. Uh, so just to tell the program where to find the files. Example data. Don't pay too much attention to what are the different inputs, because as I told you, I'm going to devote a different video to explain exactly that, okay? But we need to change that, and we need to change this other one. If it cannot find the files, it cannot run the script. That's the basic thing. So, and what else? I think that the rest, since we have changed the basic directory, everything should be fine here. Okay. So let's see. It said that this is okay. It's not slash data. Here samples, and here that was my mistake. I forget to put the right path. So okay. Well, now it's running the script. I will explain in another video what the program does. This is just for testing the installation. Okay. It's fitting one line just for the sake of speed, and very simple Stellar library. So I don't expect this to be a good fitting. But we want to see if it runs from the beginning to the end, or if it produces any error that most probably will be related to not finding the right path, because we have not put the right path in the fitting, so in the configuration file in here. But so far, so good. Yeah, go start, and this is the message you should find. All done. Okay. So now, if we go to examples, output DAP, then there is a certain output files. This is the basic output file, a DAP file. I will devote another video just to explain that. This is just to show you that the program has run from the beginning to the end. Okay. Let's see if it has created some plots. I don't know why I cannot show this in the screen. So look like it likes. That's nothing to do with the program. So okay, that's the fitting fits just 3 pointings, so the scale of the plots they doesn't matter too much, because it's just to show you that it works. Another way to visualize that this is working it is to run it with the option plot equals to 1. This should generate some that's a different thing. Okay, Matplotlib has no attribute CMap. Okay, that has to be with my own installation of Matplotlib. That's okay. So good. It's good that this is on. It seems that I need to change that, and let's see. Let's see if it now works, or if we have to install everything. It's not a problem with the code, it's a problem with the Matplotlib version. So that's important to take a note on that for the dependencies. Okay, so let's stop that and run again, because that's not what I wanted to highlight. When you put the option minus plot equal to 1, then it's going to show you the different steps in the fitting procedure. So now it's fitting the underlying stellar continuum, finding for the best systemic velocity. And then it's fitting the dust attenuation. And finally fit the different emission lines that are fit with Gaussian functions. If you follow the previous videos, you know what I'm talking about. When all these emission lines has been fit, then this the model of the gas is subtracted, and that's what is said here. The gas fit is done, so then it's going to subtract this model and fit the underlying stellar population, and this is the result of the fitting. Colors are not the optimal. So you have the data, and in green is the best model, and in magenta is, I need to change the colors, is the residuals. So you can close it. These are the weights of the decomposition. It's a very simple decomposition. And at the end, it produces a lot of different plots. This is a summary plot of all the fit that has been done, highlighting the underlying continuum, the different lines fitted with a Gaussian function, and details of different Weyl range that allows you to weight the quality of the fitting just for the integrated spectra, but you can generate similar plots for all the spectra. There are different details of fitting of different sections that this is a relevant plot. This is the model generated assuming that the emission lines are Gaussians from the parameters derived with a non-parametric analysis. So we know that for non-parametric analysis, that's not assume any model, as I explained in my previous talk, but you can generate a model assuming that they follow Gaussians using the flags, the velocity dispersion, assuming that they are Gaussian. So let's see how it looks like, this model. In black, they are the data. So the model is not perfect when you have blended lines, as I told in my previous talk. And you have residuals are in orange, the data are in black, and the model is in blue. So for when you have non-blended lines, the model used to provide with a good representation of the data that we know. So you can inspect for the lines of your interest. Remember, this is just for the integrated spectra. For individual ones, we can, well, here you see that there are issues with the derivation of the parameters, or in here. So this allows you to remember this was not a fit optimized to provide with good results. This was a fit optimized to be fast, just to make this test. But you can visualize in here more or less how the non-parametric procedure provide data for the results for the emission lines. So, well, that was for one emission line, and it's going to go. Sorry, for one of the spectra. Actually, for the integrated one, and now it's going to iterate for all the spectra in the fit. So we are going to cut this because, there are only 5 spectra fit in this quick example. But if you have a full data set and you want to visualize, this is going to become very, very slow. So I'm going to cut that. So you can see that the program is installed and it's working. And to explain how it works, we will go to the notebook the next day. But for so far for the installation, that's all that you need to know. I will stop that here.